Okay, in this video we're going to look at something which I might call an interesting advanced arithmetic problem. So we want to take this infinite nested radical, so we have the cube root of 9 plus 9 times the cube root of 9 plus 9 times the cube root of 9 plus, and so on and so forth forever. And from that we want to subtract 8 minus the square root of 8 minus the square root of 8 minus the square root of 8 plus the square root of 8 minus, and so on and so forth. So this one's a little bit harder to get a handle on, but what we have going on here is 2 minuses and then a plus, 2 minuses and then a plus, and then it's continually nested in that way. Okay, so we'll use the following tools to show these two things converge. First is this thing called Hirschfeld's convergence theorem, which says that for a(n) bigger than 0 and p between 0 and 1, this nested exponent always converges. So this limit as k goes to infinity of a0 plus a1 plus a2 plus a3 all the way up to ak, which would be like the partial sum, if you will. I haven't put that in there because it'll just get messy. And then we have k exponents of p here. So that's going to converge if and only if we take this nth term and raise it to the pnth power, and we look at that resulting sequence and it's bounded. So that sequence doesn't need to have a limit, but it needs to be bounded. Okay, and then the next thing that we'll use is a little bit more common. It's the monotone sequence theorem, and I'm just going to put one version of it, and that says that if Bn is a sequence which is monotonically increasing, in other words, Bn is less than Bn plus 1 for all n, which is a natural number, and it's bounded above, so Bn is smaller than m, and we'll just say that this is less than plus infinity, so it's a finite thing. For all n, which is a natural number, then this limit exists. Okay, so we can obviously apply this Hirschfeld's convergence theorem to our infinite nested radical with all these 9s because we have only pluses there, but we'll have to do something a bit trickier using the monotone sequence theorem for this one with the alternating pluses and minuses. It's not exactly alternating, it's 2 minuses and a plus. Okay. Good. So now let's look at this first one. So we have the cube root of 9 plus the cube root of 9, the cube root of 9 plus 9 times the cube root of 9 plus 9 times the cube root of 9, and so on and so forth. So what I want to do here is write this in the following way. So I can write 0 out front just to make it look exactly like this. So I've got a number out front. And then after that, I have, this is plus the cube root of 9 plus, now I'm going to bring this 9 in here. Okay, good. And let's see what I get when I do that. So I'm going to have the cube root of 9 to the 4th plus 9 to the 4th times the cube root of 9, and so on and so forth. Okay, great. And then from there, I'm going to bring this 9 to the 4th in here, and we'll have the following. So that's going to give us 0 plus the cube root of 9 plus the cube root of 9 to the 4th plus the cube root of 9 to the 13th. And then I'll just write the next term down just for your information. So that's going to be plus the cube root of 9 to the 40th. So let's see how that would go. So we'd have another 9 to the 13th. We bring it inside a cube root. It becomes 9 to the 39th, but then there's already a 9 there, so it'll be 9 to the 40th. And so this is so on and so forth. And so that's going to continue going forever. Okay, so that's our sequence. So in other words, our a(n) is of the following form. And so you can check this. So obviously a0 is equal to 0. And then a(n) follows the following formula. So this is 9 to the half, and then to the 3, and then times 3n minus 1. Okay, great. But we can simplify this a little bit. Notice 9 to the half is 3, so we have 3 to the 3n minus 1. Okay, but now if we take, oh, and I should say that in our case here, p is 1/3 because we're continually taking cube roots, which is the same thing as taking 1/3 powers. Okay, so now we can look at a n to the 1/3 to the n, which is what we need to look at to decide if this thing converges or not. So notice that in this case, what we'll get is we'll get 3 to the 3n minus 1, all raised to the power 1/3 to the n. But now notice that's going to be 3 to the 1 minus 1/3 to the n. Okay? But now notice that that thing is less than 3. And that's going to be true for all n, because notice it has an exponent which is a little bit less than 1. And then obviously it's always positive, so that means it will always be bounded below by 0 and above by 3. So that means this thing does converge. So here we can write up here that this thing converges. Good. Now I'm going to erase the board, and then we will write not what it converges to, but we'll find a polynomial where one of the roots is a number that it converges to. So on the last board we determined that this thing converges, and so in order to find out what it converges to, we can do the following. We can notice that it's nested in the following way. So if we set y equal to the cube root of 9 plus 9y. So that's how this thing is nested, which tells us that we have y cubed equals 9 plus 9y, which tells us that our solution, in other words, this y that we need is a root of the polynomial y cubed minus 9y minus 9 equals 0. So in other words, it's a solution to that polynomial equation. Okay, so now that we're done with the Hirschfeld's theorem, I'll clean that up, and then I'll put the summary of this part right underneath, which is the summary of what we need for this first term. Okay, so here's the summary of this first term. So if we set this first term equal to y, we on the previous board determined that this y needs to be a root of this cubic polynomial. Now we could use Cardano's formula for roots of cubics in order to get a closed form for this, but we'll see that we'll have a trick to find the value of this without going through that rabbit hole. Okay, now what I want to do is look at this second term, which I've written out a few more parts of it here. So notice we have the square root of 8 minus the square root of 8 minus the square root of 8 plus the square root of 8 minus minus plus minus minus plus, and so on and so forth. So now I'm going to use a function in order to show that a sequence that we build, which will represent this thing, will be monotone, and so it will converge. And the function I will use is the following. So I'll have f of x equal the square root of 8 minus the square root of 8 minus the square root of 8 plus x. Okay, good. And now notice if we set a1, or let's use the letter b, so if we set b1 equal to the square root of 8 minus the square root of 8 minus the square root of 8, and then bn plus 1 equal to f of bn, and this is for all n bigger than or equal to 1, then this term will converge if and only if this sequence converges, because notice that this thing will be represented by the limit as n goes to infinity of this sequence. Okay, good. So now what we want to do from here is notice the following. So notice that the domain of f is, and so now this is not too tricky to figure out. I'm not going to show all the details. I'm just going to say that the domain is -8 to 56. Okay, so let's talk through that. So notice -8 in here gives us 0, but anything smaller than negative 8 will give us a minus sign under this inner square root, and obviously that would take us outside of the domain. And now if we plug 56 in here, we get 8 plus 56, which is 64, and then the square root of 64 is obviously 8. We get 8 minus 64, which is 0, but anything bigger than 56 would cause a negative under that radical. And then you might say, well, what about a negative under the outermost radical? But anything that would happen there would happen, is not possible inside of this closed interval. Okay, now the next thing that I want to notice is that f prime of x we can write in the following way. So this is going to be 1 over, and this is just using the chain rule. So this is going to be 1 over 8 times the square root of 8 plus x times the square root of 8 minus the square root of 8 plus x times f of x. Okay, good. And so that's not too hard to see just with the chain rule. So good. Now from here, what we want to notice is that this thing is bigger than 0 for all x in the domain here. In other words, minus 8 to 56. And we actually have to take away 8 and 56 because those would give us 0 in the denominators. And that's generally the case whenever you have something whose domain is a closed interval. You only know its derivative is going to be guaranteed on an open interval. Sometimes you get the endpoints, but not in this case. Okay, good. Now the next thing that we want to notice is that f of negative 8 is going to be equal to the square root of 8 minus the square root of 8. And I'll just say that that is approximately equal to 2.27, and then f of 56 is equal to the square root of 8, which is approximately equal to 2.83. So let's see what we have. We know that f prime is always positive, and it trends between 2.27 and 2.83. And I should say the function f trends between 2.27 and 2.83. So that means that we have a function which is always increasing. It starts at this number and it ends at this number. Okay, good. So I'm going to erase the board. I'll put that summary up there, and then we are ready to prove that this is going to be a monotone sequence. Okay, so let's see what we have so far. So we proved that f, it lies between 2.2-ish and 2.83. We had those exact numbers on the previous board, but we don't really need them. And we also know that f is increasing for all values of its domain. So that's good to know. Okay, so notice that this part right here, number 1, implies immediately that Bn is between these two numbers for all n. And so that's easy to see. We could do that by induction. Notice that B1 is between these two numbers, and then if we suppose that BK is between these two numbers, then that implies that f of BK is also between those two numbers. Great. Again, because if BK is between these two numbers, then it's in the domain of f, so we can plug it in there. But we know that f of BK is exactly equal to BK plus 1, so that tells us that BK plus 1 is between those two numbers. So in other words, this thing is bounded. So we know that we have a bounded sequence. It's bounded above and below, so we're good to go there. And then the next thing that we can do is show that it's monotone, and we can do that by induction as well. And so it's easy to check kind of by hand that B1 is less than B2, and that would be our induction hypothesis. And so that's just a simple calculation. And then the next thing that we want to do is suppose that bk is less than, or maybe we'll do bk minus 1 is less than bk for some k, and then we will apply the function f, and so that means that f of bk minus 1 is less than f of bk, and that's because f is an increasing function, which we proved by looking at the derivative. But then, by how the sequence is defined, that tells us immediately that bk is less than bk plus 1. Okay, good. So here's what we have. We have a bounded sequence and a monotone sequence. So that means we know that this thing converges. So I'll clean up the board and then we will see what it converges to, but we won't actually get a number. We'll do the same kind of game that we did over here. Okay, so on the previous board we determined that this nested radical indeed converged. We used the monotone sequence theorem in order to do that. And so now notice by kind of standard methods and also the methods that we used for this guy over here, we know that this thing will converge to a fixed point of this function. In other words, a solution to that equation. And so now what I want to do from here is notice that this equation right here, we can forget about f of x for now. We don't actually need that function anymore. We just need to look at this equation and its solution. And notice that this equation is equivalent to the following equation. So we have x squared minus 8 squared, and then minus 8, and then that whole quantity squared equals x plus 8. So whatever this converges to, it will be a solution to that polynomial equation. Notice it's quite a complicated polynomial equation. It is 8th degree. But luckily what we can do from here, and I won't do all of the gnarly details, but what we can do from here is notice that this is equivalent to the following polynomial equation. So it's x squared minus x minus 8. And then x cubed minus 2x squared minus 11x plus 23. Good. And then finally x cubed plus 3x squared minus 6x minus 17 equals 0. Okay, so now you can check if you want to that if you multiply this out, this big polynomial product out, you can regain this equation. Okay, so now from here what I want to notice is that both roots of this are less than 0, which means our solution will not come from this part. And then after that, what we can do is we can check that the roots of this equation are the following. So the roots are approximately equal to minus 3.3, 2.2, and then 3.2. But if we recall from the previous board, all three of those numbers are outside of either the lower bound or the upper bound for our bn's, which we proved. So that means the value of this nested interval needs to be a root of this polynomial. So what we need is a root of the polynomial x cubed plus 3x squared minus 6x minus 17 equals 0. Okay. Great. So now I'm going to clean up the board. I'll get rid of this monotone sequence theorem. I'll show us that we need a root of this polynomial, and then we're almost done. So, so far we have the following. We have this first term, which is this iterated nest. Okay, so far we have the following. So this first term, which is this iterated cube root involving 9s, so that is going to be a root of this polynomial y cubed minus 9y minus 9 equals 0. And then this iterated square root involving 8s with 2 minuses and a plus, 2 minuses and a plus is going to be a root of this x cubed plus 3x squared minus 6x minus 17. Now, the next thing that I want to notice is the following. So if we have x cubed plus 3x squared minus 6x minus 17, which is the polynomial which this term satisfies, we can actually write this in the following way. And so this is the same thing as x plus 1 cubed minus 9 times x plus 1 minus 9 equals 0. Another thing that we can notice is that this cubic polynomial and this cubic polynomial, so they're going to have 3 real roots, but they have 2 negative roots and 1 positive root. And you can check that again by the Cardano's formula for solutions for a cubic. And so what that means is that the roots of each of these that are positive are the values that x and y have to take on. In other words, we have the positive root of this is when x plus y is positive is the same thing as the positive root of this when y is positive, which tells us that y equals x plus 1, or in other words, y minus x equals 1. But let's recall that y was this first term and x was this second term. So what we have for this goal is that the difference of these two terms is 1. And that finishes this video.